got her PhD from the University of California, Santa Barbara in 2015, and she is currently an Einstein Fellow / ITC Fellow at the Harvard-Smithsonian Center for Astrophysics. Her research interests include EGN and reverberation mapping, galaxy evolution, and she has become an expert in developing a new method, a really interesting method for modeling the kinematics and geometries of broadline regions in EGN, and so we're going to hear a lot about that today. So welcome.
Thank you so much. All right, well, it's a great pleasure to be here and tell you all about the work I've been doing in collaboration with a number of individuals, chief among them being Catherine Greer, Michael Fosna, Brendan Brewer, Tomasu Treyu, and Aaron Barth. But I also have to give out a big hand to the amazing group of observers who participated in all of the reverberation mapping campaigns that are listed here, including LAMP 2008, the OSU 2010 and 2014, and the AGN key projects through LCOGT. So this really required a huge number of observers to go out and get these data that I'm going to show you, and I think they've basically produced some of the best reverberation mapping data sets in the world. So that's what I'm going to show you today. And the main motivation for this is a desire to understand supermassive black holes and the environments in which they live, specifically in the active phase. And so as all of you are probably aware, we think supermassive black holes live at the centers of most, if not all, galaxies, and that in their active phase, when they're accreting matter from their host galaxies, they shine as active galactic nuclei, or AGN, which means we can see them at very large distances. But because they're so far away, we can't actually spatially resolve what's going on close to the supermassive black hole. And so what I'm going to talk to you about today is how we can actually sort of replace a need for spatial resolution with time resolution, and actually still probe and resolve the inner regions around active galactic nuclei with the ultimate goal of trying to measure the masses of supermassive black holes. So that's going to be the main focus of my talk. And if you're not interested in AGN, if you're not interested in supermassive black holes, maybe you're interested in galaxy evolution. And it turns out that black holes may have something to say about this as well, through a correlation that was discovered in the local universe between the masses of supermassive black holes and the mass of the host galaxy, specifically the host galaxy bulge, such that larger black holes live in larger host galaxies. And this is a little mysterious because the scales involved are very different. The gravitational sphere of influence of the galaxy is on the order of kiloparsecs, whereas the gravitational sphere of influence of the black hole is on the order of parsecs. And yet somehow these things are growing in a way that knows about or has some relationship to one another. And so the hope is that by being able to measure the masses of supermassive black holes, not just in the local universe, we can have some handle on this part of galaxy evolution and figure out what the role of black holes really is in how galaxies build up their mass, and perhaps lose their mass too. So in order to measure black hole masses, of course, we have to, well, in the local universe, resolve the motions of gas or stars around the black hole. And one of the most impressive examples of this is actually in our own Milky Way galaxy around Sagittarius A star, where we're able to map out individual orbits around the black hole. And of course, as black holes get farther away, this becomes more challenging. But using mass measurements from the motions of gas or stars, we're able to make relationships such as this one between the black hole mass on the y-axis and some measurement of the host galaxy. In this case, the stellar velocity dispersion of the host galaxy bulge, sigma star. And so you can see that for local black holes, where we have gas or star dynamical mass measurements, they have a fairly tight correlation up to about 0.4 dex. But this is, of course, in the local universe. What happens at higher redshift? Do we still have this same relationship when we have, even more AGN and galaxy merging activity? Of course, to be able to answer any of those questions, we need a method to measure the masses of black holes outside of the local universe without having to resolve upon spatial resolution. And the way we do this is using actively accreting supermassive black holes in AGN. And so instead of having spatial resolution, we're going to substitute time resolution. And we're going to try to resolve the motions of gas or stars deep within the gravitational potential of the black hole in the broadline region, which is located here. And probably most, if not all of you, have seen a picture like this at some point or another in an AGN-related talk, But here we have the supermassive black hole and an accretion disk, and this region here is the broad emission line region. And it's surrounded by an obscuring dusty torus that blocks the broadline region from certain lines of sight. Now, the reason that we can use gas in the broadline region to give us a black hole mass is because the gas is moving so quickly around the black hole that the emission lines from that gas are actually broadened. And so by looking at a spectrum and a broad emission line, you can actually get a handle on the dynamics of the gas in the broadline region. In order to measure a black hole mass from this, however, you also need to know the size of the broadline region and how far away this gas is from the supermassive black hole. And in order to do this, we use a technique known as reverberation mapping. And this really forms the basis for all AGN black hole mass measurements. And even in objects where we can't do reverberation mapping, we use relationships derived from the reverberation map sample in order to measure AGN black hole mass measurements. So it really all comes down to this simple picture in which we have a supermassive black hole and an accretion disk and a bunch of gas that is orbiting around the supermassive black hole. And what happens is we have ionizing photons that propagate to the observer from the accretion disk, but those photons also go out to the broadline region where they're reprocessed into broadline flux. Now, the thing that makes reverberation mapping work is the fact that the accretion disk does not just give you the same flux as a function of time that's constant. Instead, it's actually stochastically variable. So if you monitor an AGN accretion disk, you can get something that looks like this, or some other variability pattern. And that means that if you also monitor broadline flux from the broadline region, you should see exactly the same sorts of features, but with some time delay, tau, that depends upon the light travel time of these photons out to the broadline region and to the observer. And so this is what gives you some scale for the broadline region and allows you to do reverberation mapping and in the end get a measurement for the black hole mass. Okay, so in order to actually get this mass measurement, we take the width of the broad emission line, V, and we get the time lag, tau, from reverberation mapping, and we measure a mass. And so C is the speed of light, G is a gravitational constant, and this final thing, F, is a normalization factor. And what this normalization factor does is it encapsulates all of the detailed geometry and dynamics and orientation of the broadline region. Unfortunately, because we cannot spatially resolve the broadline region, we don't know what any of this stuff is. And so determining F becomes the biggest challenge in trying to reduce the uncertainties in reverberation mapped black hole mass measurements. So what we do in practice is we take the M sigma relation that I showed you before between the black hole mass and the stellar velocity dispersion of the host galaxy bulge for inactive local galaxies with gas or stellar dynamical mass measurements, and we overplot on them the reverberation mapped masses and make them align with one another. We assume that they have intrinsically the same M sigma relationship, and that gives us an average value of F that we can then use to normalize the entire reverberation map sample. So that works incredibly well statistically. The problem is that if you look at any individual reverberation mapped measurement, there is a sizable uncertainty that could be as large as the scatter in the M sigma relation. So you could have an additional uncertainty that's up to 0.4 dex, which is a factor of 2.5, in your black hole mass measurements. And compared to these red points, stellar and gas masses have significantly smaller uncertainties, at least statistical uncertainties. I'm sure Janelle could tell you all about that. Yeah, we would really like to have smaller uncertainties than a factor of 2.5. Okay. But of course, one of the things you can look at here is that you need a fair amount of data in order to get a reverberation map measurement. Okay, you have to monitor AGN and hope that they are variable on the time scales that allow you to probe the broadline region. And this is somewhat problematic if you want to get thousands of AGN black hole mass measurements. But thankfully, reverberation mapping has given us a relationship that allows us to measure black hole masses much more easily. And this is the radius luminosity relationship, the relationship between the size of the broadline region and the AGN luminosity. And what this means is that you can, in a sense, take a single spectrum of an AGN that has a broad emission line and actually get a mass from that single spectrum, instead of having to monitor an AGN over months or perhaps for high luminosity AGN even years, okay? So this allows us to make single epoch black hole mass measurements as long as you're willing to have a small additional uncertainty. So the scatter in this relationship is about 0.16 dex. So as long as you're able to incorporate that additional uncertainty, you can get black hole mass measurements for thousands of AGN, as many as you can get spectra for. Unfortunately, you still have the large uncertainty that is from the unknown structure of the broadline region. So what I'm going to talk about today is how we can get around this and try to reveal the hidden broadline region that we cannot spatially resolve to try to answer some of these sort of unknowns. And the way that we're going to do this is by modeling high-quality reverberation mapping data directly using a geometric and dynamical model for the broadline region. And what this is going to give us is the three things that we really want. The first is actual quantitative constraints on the geometry and dynamics of this region, including correlations. We're going to work in sort of a framework of Bayesian inference. So our goal is going to be to get posterior PDFs for all of our model parameters and their correlations. But this, of course, also means that we are, in a sense, measuring the value of f, this normalization constant, for individual objects instead of having one average value. Finally, it's also a model parameter, the black hole mass. So because we don't have to normalize it using some average value of f, we have a hope of measuring it to less than 0.4 dex uncertainty. And so these are our aims. And in the next couple of slides, I'm going to tell you about how we go about doing that before showing you some results. Okay, so the first step to even see if this method would work was to develop a simply parameterized phenomenological model for the broadline region, where we're only interested in trying to model the distribution of emission. Let's forget about the distribution of actual gas for a moment, although it's related to the distribution of emission by photoionization physics and other interesting things that we do, in fact, care about. But for now, let's just worry about the emission. And we're going to model its density, or the amount of emission, in a given physical and velocity space by a bunch of point particles, okay? And each of these point particles is just going to simply act as a mirror, okay? And it's going to reflect the continuum emission from the accretion disk located at the origin. It's going to reflect that emission to the observer with some time lag that depends upon its position, and with some wavelength shift of the emitted line flux that depends upon the point particle's velocity, okay? So that's the simple picture. Of course, that takes a couple of different pieces in order to be able to put it together. And the first is the fact that we need to know what the AGN continuum is doing at all times in order to calculate the amount of line flux from all of these point particles. And so the first step is to model the AGN continuum light curve using Gaussian processes, and this allows us to also incorporate the uncertainty and the interpolation in our final inference. The second piece is to actually define some model for the geometry and dynamics of the broadline region, because we have thousands of point particles, and we do not want thousands of actual parameters. That would be totally unsolvable. So what we do is we take this continuum light curve and we filter it through this distribution of point particles, and we get a model spectrum as a function of time that we can actually compare to real data. And by exploring the parameter space, we can figure out what our posterior probability distributions are on all of our model parameters. So you can see here in blue and green, basically for those of you in the back, it's right underneath the red lines, which are the model. So for one example that I'm showing here, the fit is excellent, even with a simple model. And our, of course, other goal is just to be able to model the overall variations of the line flux. Okay, so not just the velocity resolved behavior, but also the overall variations in flux. Okay, so now so that you understand the kinds of things that we want to know about the broadline region, let me just very quickly go over some of the parameters in our model. So we have things like an opening angle of the disk and an inclination angle, and we also have some asymmetry. So you could have a midplane of your disk that's opaque. Imagine if there's really, really dense stuff in the middle that's somehow not illuminated. And we also allow for more emission from the near or the far side of the broadline region, and I'll show you a picture of what that looks like in just a couple slides. But you can think of it sort of as phases of the moon in terms of whether things are sort of illuminating more back towards the central source or back out the other side of the cloud. And then we also allow for more emission from sort of the faces of the disk. So instead of having a full disk, you have something that's more like a cone. Then for the radial distribution of emission, we use a flexible gamma distribution. So this can range from a narrow Gaussian to an exponential profile or even steeper. So the goal is to include as few assumptions as possible from the beginning, because we really don't know what should be going on. For the dynamics, we've chosen something that is similarly simple. We allow for some near circular or elliptical orbits combined with either inflowing or outflowing orbits. And so this is it. This is the model that we use. And so first I want to tell you about what the geometry is that we infer from actual data. And I'm going to focus exclusively on the H-beta broad emission line because this is what is used pretty much with all of the best data sets cover this line. It's the easiest to sort of calibrate, and there's just a lot of really good data for it. So the first data set that we analyzed was actually the LAMP 2008 data set from the LIC AGN monitoring project. And Janelle Walsh actually played a very big role in making this data set. And so what we did was we went through and we modeled the top or most high quality 5 AGN in this sample. And we were able to constrain the broadline region pretty well in those 5 cases. And you can see what the geometry looks like in this figure here. So in the left-hand column, I'm showing you sort of an edge-on view of what the broadline region looks like. So you can see the inclination angle and the opening angle of the disk. And the observer is looking from this direction, from my direction. And the size of the point particles tells you how much emission is coming from each point. So for example, if you look in this panel here, the points on this side are bigger. So that would be more emission from the far side of the broadline region, as though the gas is preferentially re-emitting back towards the central ionizing source, which is actually something that photoionization physics calculations predict. So you can see that in general what we're finding is that the broadline region is a thick disk viewed close to face on. And the close to face on is actually important because, as I mentioned at the beginning, in our picture of AGN we have this dusty obscuring torus, which is supposed to block our sort of view of edge-on systems. So we actually expect these guys to all hopefully be face on. And if they were edge-on, it would be sort of weird, right? And we wouldn't exactly know whether something was wrong with our model or maybe there were objects that didn't have dusty obscuring tori. The other thing that we find with this sample is a preference for more emission from the far side of the broadline region. As I mentioned, this is consistent with photoionization calculations. And it's interesting that we would find something like this without having sort of any assumptions whatsoever about actual photoionization physics. And when we combine this with the dynamics, which I'll show you in a couple slides, we're able to actually measure the black hole mass in these 5 objects to within 0.15 to 0.3 depths uncertainty, depending on the data quality for these light curves. So for ARC-151, which is the object I showed you an example of the model fits to the data a couple slides ago, this is at the top, and this is the best object out of these 5. We can actually measure the black hole mass to the 0.15 depths uncertainty. So this is substantially better than the 0.4 depths uncertainty we would otherwise have to have if we use an average value of the F factor. So after this initial success, we went ahead and started working with a number of people on trying to apply this method to a whole slew of other data sets. So the first person I started working with was Catherine Greer, who's currently a postdoc at Penn State. And so she did, as part of her PhD thesis at OSU, she was in charge of the OSU 2010 reverberation mapping collaboration. And so we've been modeling 4 of her best objects, shown here. And so you can sort of see the outside here because it's zoomed out by a factor of like 6 compared to these panels. But you can see that in general, for these 4 objects, you're still seeing sort of a close to face on, thick disk. And it's interesting to have these 4 objects because they are higher black hole mass, higher luminosity, and slightly higher redshift. than the LAMP 2008 object. So it would be really nice, right, to model as diverse a range of AGN as possible to see if you find any correlations there with things like AGN luminosity. But this sample is also very interesting because it has 3C120. And 3C120 actually has a radio jet. And people have measured the inclination angle of that radio jet, which means that we can actually try to compare what we find in our broadline region modeling with some other results that give us an idea of the orientation of this structure. If we assume that the radio jet should be sort of perpendicular to the plane of the accretion disk and the plane of the broadline region, then we would hope that we would measure the same inclination angle as you do from the jet. And in fact, we end up doing exactly that. So it does seem like things are more or less sort of aligned with one another, and it also suggests that the inclination angles we're measuring are hopefully actually physically real, despite the fact that we're using a fairly simple model for the broadline region. So even more recently, I started working with Michael Fosnon, who's a finishing graduate student at OSU, working with Brad Peterson, and for his thesis, he worked on the OSU 2014 reverberation mapping dataset, and there will be at least 2 objects in that sample that we can apply this analysis to. And one of those, NGC 2617, is interesting because it's one of these changing look AGN, where in previous images you pretty much saw no broadline emission, maybe a little bit in H alpha. And then all of a sudden, the broadlines appeared and were extremely strong enough to do reverberation mapping on. And so it will be very interesting to see how the geometry and dynamics in this object compare to the rest of the sample. And maybe we'll be able to model some additional changing look AGN. Okay, so now that I've shown you the geometry, which in general looks really consistent amongst these 10 objects, I'd like to talk about the dynamics. Okay, and so what we get for at least these 10 is a range that goes from totally dominated by inflow to pretty much just elliptical orbits. How many of each do we have? Well, it turns out that we have a ton of inflow. So inflow is highly preferred in these 10 objects. And yes, you would expect to see some inflow, right? Things are, in a sense, channeling down to the black hole. But you wouldn't necessarily expect to see so much radial inflow. So this is something that we would like to understand further, and whether it's some part of maybe an outflow that's happening in other regions, maybe in other broad emission lines. So this is something that we're sort of still trying to understand. Okay, so then finally, I want to talk about how robust these results are, because we're using a fairly simple model, and despite the fact that in one object we have an agreement between the radio jet and the inclination angle of the broadline region, what other tests can we do to prove to ourselves that we're actually getting something meaningful? Well, one of the tests we can do is to try to apply this approach to 3 completely independent reverberation mapping data sets. Because in that sense, you would expect certain things like the inclination angle and the black hole mass to stay constant, even over 7 years, which is the time scale spanned by these data. So for ARC-151, we have data from LAMP 2008, LAMP 2011, and the LCOGT AGN-P project. And you can see that in all these data sets, the AGN was extremely variable. So here's the continuum light curve for each of these, and the H beta light curve. And you already basically saw this one a couple of slides ago. And then you see examples of the emission line profile in each of these cases with the model fit in red. So in each case, we're able to model the data fairly well. And what ends up happening is that we get an incredibly consistent picture of what the broadline region is doing for these 3 different data sets. The one thing that has changed is that presumably the luminosity has changed, and the entire broadline region has grown by a factor of almost 2. So it's radially increased, as we would expect from the radius-luminosity relationship, but otherwise, the structure that you see is very similar. And for those of you who like looking at posterior PDFs, I couldn't help myself. So these are posterior PDFs for the various model parameters, and I realize you probably can't actually see what the different parameters are. But the 3 different colors are the 3 different data sets, and for almost all of these parameters, you can see that they lie pretty much smack on top of one another. Now, some of the data sets have a harder time constraining various parameters, especially having to do with the asymmetry of the geometry. But these are really hard things to be able to constrain in other objects as well. And it's totally understandable that certain data sets and certain variability features would be able to better probe certain parts of the broadline region. But for something like the black hole mass, which is this panel, you can see that they lie pretty much exactly on top of one another. And if you combined the three posterior PDFs and assume they're independent data, so you multiply their likelihood functions, you can actually get a black hole mass that has an uncertainty of only 0.1 dex. Okay, so this is like a factor of 2 better than our 0.4 dex that we originally started with for this object. And the one thing you'll notice that is different is the size of the broadline region. So it's increased from about 4 light days to out to almost 7 light days or 8 light days. Okay, so it's grown, but its structure has not really changed. And I think this is showing us that while we may not have a very complicated model for the broadline region, we are able to consistently get exactly the same sorts of behavior out of completely independent data sets that have nothing to do with one another otherwise. Okay, so finally, I wanted to talk about the big picture and how being able to model the broadline region and measure black hole masses more precisely in reverberation mapped objects sort of affects the sort of larger picture of both AGN science and perhaps a little bit galaxy evolution, starting with the M-sigma relationship. Okay, so here I'm showing this yet again. Here we have black hole mass on the y-axis and stellar velocity dispersion of the host galaxy bulge on the x-axis. And these blue points are similar to the red points I showed you earlier in that they're the local dynamical black hole mass sample using either stars or gas. And these 5 blue points are the 5 objects from the LAMP 2008 sample that have actual independent black hole mass measurements. So we can just plop those down there. We don't need to normalize them using anything. And you can see that they seem to lie right on top of the relation, okay? So we're not seeing some offset between AGN and the local sample of supermassive black holes. And as we increase the sample and get more sigma measurements of different objects, we should be able to fill this in and figure out whether we see larger, smaller scatter, see what's happening. And it also means that if we can do reverberation mapping in higher redshift, we can actually start to look at evolution in the M-sigma relationship with black hole mass measurements that are not humongous. Because if you look at current work that's trying to look at evolution in the M-sigma relationship, pretty much the only thing you have to work with are those single-epoch masses, okay? And that means that their uncertainties in the black hole mass are pretty large. So that brings me to how this work can affect those single-epoch black hole mass measurements, which, to remind you, rely on this relationship between broadline region size and AGN luminosity. And I think there are 3 main ways that we can do this. The first is to test a basic assumption that we all make, which is that you can use the local group of reverberation mapped AGN to make a radius luminosity relationship for H beta, and then apply that to higher luminosity quasars at high redshift, including using different lines like carbon-4 and magnesium-2. Okay, and you can try to calibrate this, but we're assuming that the dynamics and perhaps even parts of the geometry are the same. And it's not at all clear that this is the case, because if you have a higher luminosity AGN, then not only are you moving your broadline region out, but you may be changing the ionization field such that you can drive outflows and actually change the dynamics of the gas that's giving you the broad emission lines, which means that your dynamics may not be just due to the gravity of the black hole. There may be some other effects that play in as well. So that's one thing we can do, and this is something we're going to be able to do very soon, because there are actually 2 different reverberation mapping programs that are in progress right now to look at more luminous AGN so that we can start to test these things. The second thing we can do is actually try to make an independent measurement of the mean value of the F factor without having to assume the M-sigma relation at all. And of course, with 5 objects from LAMP 2008, the uncertainties are humongous. But as we start to increase the sample by a factor of 2 or 3 or 4, hopefully soon, then we can maybe start to actually have a value that has smaller uncertainties. And finally, what would be even more interesting is if we can come up with some parameter of a broadline region or of an AGN that correlates with this normalization factor f. Okay? So if we could have some way to measure the value of f more precisely, then we would be able to reduce our uncertainty in the black hole mass. And if we didn't have to do reverberation mapping in order to get the value of f, that would be incredibly time-saving. And so what we've been looking at is correlations of f with different properties. And the strongest correlation we've found so far is between the value of f and the inclination angle and opening angle of the disk. And this makes a lot of sense, right? Because the inclination angle and opening angle of the disk are what determines the black hole mass, right? And sort of how much of that you see. So there's sort of a tight degeneracy between those three parameters. So it's not too surprising that you see similar effects here with the f factor.
I think I'm not just thinking, don't you have like a prior on the range of f from real theorem type arguments?
We do not include any prior in f. F is something that comes, so here's the way it's calculated. We model our systems and we get a black hole mass. We then take that black hole mass that we've measured and we compare it to the virial product that's measured using reverberation mapping and back out what f is. So we're actually not assuming anything about the rest of sort of how the virial product is estimated or anything.
Okay.
Yeah.
And your mean value of f is similar to the f's that you would get.
Yeah.
Or-
Yeah, and you could sort of see that, right, in looking, here, right? I mean, there's no humongous offset, so things look totally consistent with your black hole mass measurements. Okay, so finally I just want to talk about where we can go from here. And there are definitely some unanswered questions. One of which is, how does the broadline region emission relate to the actual underlying gas? At the very beginning I said we were going to ignore that because it's hard, and that's still true. But we can actually use photoionization modeling to try to make a new model for the broadline region that incorporates those sorts of constraints. And it's actually very interesting because photoionization modeling in some ways will shrink the parameter space that we currently allow. I mentioned that we found more emission from the far side of the broadline region. That will be much more constrained if we actually assume things about photoionization modeling. But this will allow us to go back and forth between the space of an actual emission line profile that we see and a distribution of gas. The second question is whether parts of the broadline region probed by different broad emission lines give us the same picture, how the broadline region changes as a function of radius. So just to give you some examples, if you have sort of the broadline region radius, you get carbon-4 that is emitted closer to the accretion disk than H beta, and then H alpha is sort of even farther away. And so by modeling different emission lines, we can actually sort of map out the entire broadline region as a function of radius as far as it may go. And so there are multiple data sets that now have monitoring of multiple emission lines, including the AGN Storm data set that was monitoring NGC 5548, both in the optical, so you get H beta, but also using HST, okay, to get carbon-4 and Lyman alpha. So this proposal took like 10 years to get accepted because it involved a crazy number of orbits, okay, in order to monitor this object. But now we have, the AGN Storm data set is the best reverberation mapping data set we have and will probably have for some time, just because of its incredible multi-wavelength coverage. But we also have an ongoing campaign with LCOGT to look at many different AGN, where the redshifts are chosen such that we both have H beta and magnesium-2, or magnesium-2 and carbon-4. So we can finally start to compare these different broad emission lines that we use for black hole mass measurements at higher redshift. Okay, and then for a final question, we would really like to see whether any broadline regions actually have signatures of outflows, because all of the broadline regions I've showed you so far have signatures of inflows. But if you talk to most AGN astronomers, they often will have a pet outflow theory that they think the outflow is coming from one specific region, or maybe many, different regions. But you can see theories of outflows that generate anywhere from the accretion disk through the broadline region out to the obscuring dusty torus. And it's possible that you do have outflows in all those places. I guess it may be possible that you have them all at the same time in one source, but it would be very interesting to see if we can see any signatures of that in the actual broadline region. Because if we do, then this sort of modeling approach could give us a handle on actually trying to figure out what the properties of that outflow is. I mean, we know that black holes are interacting with their host galaxies via some mechanism, right? And it would be really nice to be able to understand the nature of possible outflows at their source, where they're actually being launched. Okay, so in conclusion, broadline region modeling of reverberation mapping data allows us to measure AGN black hole masses more precisely, considerably more precisely than 0.4 Dex uncertainty. It also allows us to make the first measurement of the normalization factor for the black hole mass, F, in individual AGN. And it, of course, also lets us constrain the detailed geometry and dynamics of the broadline region in a statistical way. And so we've published results for 6 objects with many more in progress. I think within even the next year, that sample will have grown by a factor from 5 or 6 up to something like 15. And in general, this is a flexible framework in which we can test different models for the broadline region. And I'm currently working on trying to develop a photonization physics-based version so that we can start to see how this affects the gas as well. So that's it. Thank you very much.
So, the lines that you use are using HV primarily.
Yeah.
So, I don't know, maybe I missed it, but is there, I always thought there was like 5.07, and you also showed H alpha and C4. And obviously it depends on what's successful, but like in your platonic ideal, what would be the ideal line set that you would use for this?
Yeah, so H alpha is difficult because it's hard to calibrate different spectra relative to one another. H beta is great because it is the narrow O3 lines right next to it. And so you know that the differences between consecutive spectra in your light curve have been normalized relative to one another. And since that's what everything is based on, is looking for variability features, it's incredibly important that you can actually sort of, get your different spectra on the same scale, right? And so H alpha is hard because there aren't those strong narrow lines there. What I would really like to do is use H gamma, and sometimes you can see H delta. Those are a little bit trickier, both because they should be coming from gas that's a little bit closer in. And so sometimes certain data sets don't have the temporal resolution to be able to really resolve that. But certain data sets, for example, the AGN storm data set that has HST monitoring, they also have things like helium-2, which is much closer in, and in every single data set, it's pretty much unresolved. But finally, we're starting to be able to resolve it with this HST data. So really what I would like is I would like to have both UV respirant coverage and optical coverage in order to get carbon 4, carbon 3. Lyman alpha gets tricky because of absorption, magnesium 2, H beta. I mean, if you could get all of the main broad emission lines, that would be fantastic.
So I guess if you brought it, obviously do you need near infrared
I mean, as long as it's coming from the broad emission line region, then you could see. I just don't know. I have not looked at any data in that range, so I'm not sure what the signal to noise ratio is. I mean, this requires very high quality data. So that's really the one constraint.
Any other questions? I'll ask them then. So, I mean, I think it's great that you've built up this model over the years. You wrote this little toy model to begin with, and it's great that you're adding in the photoionization stuff now. So, beyond that, I mean, is there any next steps in the model, or are you satisfied with the model and it's now about applying it to as many AGN diverse galaxies as possible?
So I think it's a combination. I definitely want to apply it to as many objects as possible, but I think the ways that I would like it to grow, in addition to the photoionization modeling, is to, if we can find objects where we see outflow, then we would like to be able to have a more physical model for outflow. And there are tons of different outflow models. So I think if we can put together a sample of objects that show outflow signatures, we could spend indefinite amounts of time trying to test different outflow models. with the data. So that's one direction. I mean, I think really, especially with the photoionization physics, what's going to be extremely powerful in terms of constraining the actual physics of the gas is using multiple emission lines simultaneously. And the reason for this is that if you're going to assume something about the gas, such as its emissivity as a function of radius, its responsivity to changes in the continuum as a function of radius, these things are somewhat degenerate in things like column density and the distribution of gas densities you assume in some parcel of gas. But if you have multiple emission lines, each with different emissivity and responsivity curves, you can start to sort of, cut through the parameter space and actually constrain things like what is the distribution of densities in a cloud? Is the traditional thing that we do where we assume a wide range of densities in any given cloud, is that actually true? So these are the sorts of things that I'd like to test. So sort of a combination of more data, more lines, and better models.
So I had a quick
Yeah.
follow-up. So how do you, like the outflows and inflows, how do they manifest themselves in your observations?
Yeah, so they will often manifest themselves in asymmetry in the emission line profile, but it's not just that. I mean, really what we're sensitive to is the variations in the emission line profiles and how they change as a function of time. And whether, if you have a big increase in the continuum, you see an increase in the wing of the line on one side versus the other. So it's sort of this complicated, it can be hard to visualize.
So,
Yeah.
Sorry, as a quick follow-up. Okay, so if you had the choice between more data or better quality data on the objects that you have, which one would you choose?
Ooh, and
Both.
that is an
These are the only
excellent
ones.
question. That is an excellent question.
Just say
And
yes.
Yeah, well, other than just saying yes, I think actually we currently have data that's of perfect goodness for the complication of model that we have. This HST reverberation mapping data set I keep mentioning, AGN Storm, the data are actually so good that I think we're going to have to really analyze them using the photoionization modeling. Right now I'm binning the data by quite a bit in order to get things to run quickly. So there's also an element of numerical advancement in terms of parallelization, because analyzing each of these AGN takes multiple weeks on, say, 8, 10 cores.
What, you're not running these on supercomputers?
I can do that too, but even then it takes like a week, and the queue times are long. So I mean, this is not something you can do in an afternoon and get an answer. So basically, how this has progressed is as we get more computational power and the data quality has improved, we have then improved the models so that they could match the complexity of the data. So I think what's actually going to happen in the future is that the two are sort of going to increase in step, right? We get better data, we have to develop better models to be able to match the complexity. And then, of course, you want to get continued better data. So yeah.